Pulsars are supposed to be reliable, cosmic lighthouses with a steady beat. Yet some suddenly go quiet, then return as if nothing happened. The first question is obvious. Did the star turn off, or did our line of sight lose the beam? Tonight's case is Pulsar. Nulling. Silence that behaves like a switch, not a slow failure. Nulling is defined as radio pulses that abruptly disappear for a number of rotations, then suddenly return. The neutron star keeps spinning. What vanishes is the detectable radio emission. That's why nulling is not the same as a pulsar dying. It's a change in emission visibility or emission physics. The key clue is the abruptness. It looks like a mode flip. A pulsar's radio voice is driven by an electrodynamic environment, plasma, currents, and open magnetic field lines. If that current system reorganizes, the radio emission can change without the star changing. So the crime scene isn't the core, it's the magnetosphere. This frames nulling as a circuit problem. The engine can shift states. One of the most important discoveries is that some pulsars switch between two spin-down rates, and those switches track changes in radio pulse shape. That ties timing noise to emission states, meaning the braking torque changes when the emission state changes. It's evidence that the magnetosphere can settle into distinct regimes. This doesn't just look like silence, it changes the star's measurable slowdown. Intermittent pulsars take nulling to the extreme. They can stay on for days, then off for days, repeatedly. In PSRB 1931+24, the on-off cycle is quasi-periodic and the spin-down differs between states. Classic evidence that the magnetospheric current system changes, not just the beam direction. This is the closest thing to a smoking gun, that silence can be a real physical state. A competing explanation is purely geometric. The star is still emitting, but the beam no longer crosses Earth. Small shifts in emission height or beam shape could move the cone enough to hide the pulses. Geometry can imitate off, so the investigation splits. Which cases are true emission shutdown, and which are beam miss events? If a pulsar is off at one frequency but still detectable at another, that points to changing emission regions rather than total shutdown. Multi-frequency observing is a practical test. Broadband silence suggests a deeper magnetospheric change. Selective silence suggests geometry or altitude shifts. In other words, frequency behavior is a fingerprint. That's why wide-band surveys keep reshaping this field. Radio emission depends on plasma supply, especially electron-positron pair cascades that feed the magnetospheric circuit. If that supply drops below a threshold, coherent radio emission can collapse. When conditions recover, emission can snap back. This makes nulling look like fuel starvation inside an otherwise intact lighthouse. Observers quantify nulling with nulling fraction, how much time a pulsar spends silent. Many nullers have small fractions, some are extreme. This matters because it hints at different underlying mechanisms, brief dropouts versus long-lived alternate states. If silence were purely random noise, we wouldn't see stable, characteristic fractions tied to specific objects. Rotating radio transients, RRATs, were discovered as isolated bursts rather than steady periodic signals. One interpretation is that at least some RRATs are extreme variability cases, mostly off, with occasional detectable pulses, or always faint with rare spikes above detection limits. They sit on the border between nulling, mode changing, and survey sensitivity. RRATs force an uncomfortable question. How many silent pulsars are simply too faint most of the time? Mode changing means the pulsar still speaks, but the pulse shape changes. Nulling is when the detectable emission drops near zero. Many researchers treat them as related expressions of the same state switching behavior, different outcomes of the same magnetospheric rearrangement. That's why you often see them discussed in a single framework. People often assume silence means a pulsar is dying, but nulling can occur in objects that aren't simply approaching a permanent shutdown boundary. Temporary silence behaves like a reversible state, not a one-way decline. The story isn't end of life, it's system switching. Nulling isn't declared by a single missed pulse. It's measured statistically through pulse energy distributions and stacked sequences. Observers look for bimodality, bursts clustered in one state, silence clustered in another. For long nulls, they track whether timing and spin-down behavior also changes. This is slow surveillance science, not a viral moment. Abrupt transitions are the biggest clue. They imply the system has multiple stable configurations, like a circuit with discrete modes. That's hard to reconcile with a simple gradual weakening model. If the magnetosphere can choose between states, nulling becomes a predictable outcome of stability and instability, rather than random failure. Recent work has continued exploring how geometry and state changes may connect across intermittent and state-changing pulsars. The key point is not solved, but sharpened. The same star can change both what it emits and how we intersect its beam. Geometry can amplify what a physical state change looks like to an observer. That means silence may be a combined effect, not a single cause. The cleanest working picture is a three-part model. Magnetospheric state switching is the core, plasma supply influences which state is stable, and geometry determines whether we detect it. Different pulsars may weight these factors differently. That's why nulling looks like one phenomenon but behaves like a family. In a field like this, the best model is the one that predicts what observers will measure next. Pulsars are used for precision timing and tests of physics. But if pulse shapes and spin-down rates can switch, that introduces systematics observers must account for. Nulling isn't just a curiosity, it's a stability problem. Understanding switching improves how confidently we use pulsars as tools. We still can't point to one universal trigger that explains every nuller. Some look geometric, some look plasma limited, some show torque link switching that screams magnetospheric state change. The same symptom, silence, may have multiple roots. That's why nulling remains a live case file in astrophysics. A pulsar that goes silent hasn't vanished. It's still spinning, still magnetized, still there. The evidence increasingly points to switching, sometimes in visibility, sometimes in emission physics, sometimes in torque itself. If it sounds impossible, we investigate it, because the next dataset might reveal what flips the switch.